All right. So, good evening, everyone. I am Samarth Patel, founder and CEO of the Indian Space Society, and I welcome you all on behalf of the entire ISS family to this webinar on astronomy-based internship, which also takes into account several other important engineering aspects also. So, starting with, I hope everyone is safe and sound in this environment. Now, let me lay out some basic rules to be followed by everyone during this webinar. First of all the participants here present in the Zoom meeting are not allowed to unmute themselves. You will be allowed to chat in the chat box once the Q&A session starts. And I request everyone not to disturb the environment, the ambience once the webinar starts with our guest speaker. So there will be a Q&A session at the end of the webinar where we will try to take in as many questions as possible within a time frame, obviously. So participants present here in the Zoom meeting are allowed to type in their questions in the chat box, that whatever you want to ask, while participants attending the event through Facebook Live are requested to type in their questions in the comment section. Now, I strongly recommend everyone not to spam the chat box or comment sections with the repeated messages. Do not do that. And as I said, we'll try to take as many questions as possible. So I hope everyone understands the instructions that are given to you. Now, coming to today's guest. So today we have with us Miss Sanchita Abrol, and she is a mechanical design engineer working with Boston Scientific, India. She is a part of their urology and pelvic health division, wherein she designs medical devices and products. So apart from being a mechanical design engineer, Sanchita has a strong parallel interest in astronomy. She has been a dedicated amateur astronomer right from her school days, where she was selected to compete, and she even won a gold medal at the Mission to Mars themed competition held at NASA Space Center, Houston, Texas. And she has completed her BTech in Mechanical and Automation from IP University, Delhi, and her MTech in Mechanical Engineering under TEQIEP scholarship from Maharshi Dayanand University, Haryana. Soon after she completed her MTech, she was chosen to be an intern at Aryabhat Research Institute of Observational Sciences for a period of 4 months. We are happy to have you on board with us with the Indian Space Society, and we would love to hear more about your internship experience. So I welcome Ms. Sanchita Abrol. Yes. Yes,
Yeah,
Sanchita. So there was a
got it.
problem with yeah,
All
muting the
good.
participants. So
Yeah.
yes, please, the stage is yours.
Thanks a lot, Samar. That was a very kind introduction. And I welcome you all to webinar. I am really happy to be here and to share my experience with all of you. And before I begin, I'd just like to share my screen. Samarth, I think you'll have to enable me to do that.
Yes, please.
Sure. So I hope it's coming up.
Yes, you are good to go with.
Great. So one request from my end to all the people who've joined in is that during the webinar, I would be talking about multiple courses and modules that you can take online. But don't worry, you don't need to write them down. I do have a slide in the end that has all the relevant links. So please feel free to sit back, take a deep breath, and let's make sure that the session is both interesting and interactive. So, here is an overview of what we would be discussing today. I would like to start by sharing my journey as an astronomer. followed by details about the visiting student program at ARIES. ARIES, that is the Aryabhatta Research Institute of Observational Sciences. And I will be talking in detail about the objective of the internship and how I met those objectives. Lastly, we'll be looking at the results and I'll give my final words for the webinar. So without further ado, I would like to start by talking about my background. So my interest in astronomy dates back to my school days, as Samarth has mentioned. I was part of the Space Astronomy Club module in my school. For those of you who don't know about space, it is an NGO that ties up with schools for astronomy related modules. However, they do have courses that you can take from all across the country, which I recently checked. Apart from this, I have also been associated with Nehru Planetarium in New Delhi through AAAD, which is the Amateur Astronomers Association of Delhi. You can check online if you have similar associations working in your city for space enthusiasts, where you can become independent member and connect with more people in this field. So in my 12th standard, I got selected and won the Mission to Mars themed competition at NASA Space Center, Houston. The competition involved being a part of space and technology oriented workshops, building model rockets, and a Mars rover alongside meeting scientists and former astronauts. Now, this next one is an important event. The All India Asteroid Search Campaign is held for school and college going students, along with independent members to participate in asteroid hunting. When I say independent members, it refers to people who are currently either looking for a job or working somewhere. So in this campaign, you need to analyze pictures and data for identifying near-Earth objects and main belt asteroids. If your discovery is confirmed, there are many accolades that wait on your way. In 2016 to 17, while I was completing my master's, I took a number of courses on online learning sites such as EDX and Coursera, and it greatly helped me accelerate my learning curve. One of the most interesting courses that I took was a hands-on introduction to engineering simulations, which is still available on EDX. If you're interested in learning basic and this simulation, this is a great course to take. I cannot recommend this enough. And at last but not the least is the visiting student program at ARIES, and I will be talking in detail about it. In the pictures, you can see on the left that the ARIES optical telescope is in the background. The one on the right is my picture inside the dome of the Devsthal optical telescope, which is Asia's largest telescope and also the main focus of my project that I completed there. So going on ahead and going to talk about the visiting student program at ARIES. So ARIES is one of the leading research institutes in India, and it specializes in two domains. The first one is observational astronomy and astrophysics. The second one is atmospheric sciences. The main research in the astronomy and astrophysics division includes many fields of studies like the one that I've mentioned here: solar, planetary, stellar, galactic, extragalactic astronomy. All these research areas are available to be pursued on the ARIES visiting program. So they accept applications from BTech final year, masters, and PhD students for summer projects and thesis completion under guided faculties. Now, one important thing to note is that you will have to check their website for an update, because I recently checked the website and it showed that they are postponing this program for this year due to COVID. But ARIES is not the only institute in India that offers such an opportunity. Indian Institute of Astrophysics, IIA, IUCA, and several IITs also have programs. especially IIT Indore, where they have recently set up a facility for radio astronomy. And don't worry, the link for these programs are there in my last slide. So let's begin the most important part of the webinar, that is to talk about the Aries project in detail. Now, before I start with the project, there is a simple phenomena that we need to understand. This phenomena is called astronomical seeing. So, seeing is one of the biggest problems for Earth-based astronomy. It is the apparent blurring or twinkling of faraway objects like stars due to turbulent mixing of Earth's atmosphere, which results in change of the optical refractive index. So, keeping the jargon aside, let me tell you a story about it. In 1977, Italian astronomer observed Mars and found that it has some canal-like features, which not canal exactly, it's canal-like features on its surface. So this was a time before the use of high-resolution telescopes. So there was no way of capturing the image, but record it by drawing it. So years after, one day, was another astronomer called Percival Lowell, who found these drawings and started claiming that these canals were indeed made by Martians, the green-eyed Martians that we see on television. So this news got a lot of media attention, only to find that this misunderstanding was due to the effects of astronomical seeing. So it's not just an old story. NASA spent a lot of money each year to ensure that there is little to no seeing in our ground-based telescopes. So to measure it, there is a term called full width at half maximum. Where it comes from is a whole other question, but for now you can note that when your FWHM is less than 1 arc second, it is said to have excellent seeing, and when the objects are bright and focused. On the other hand, if your FWHM is greater than 2 arc seconds, the seeing is said to be poor. That means your images are blurry and out of focus. Here you can see the image showing how a point object and the moon's surface look under extremely poor seeing conditions. It is difficult to make out the actual position of these objects that are there in the night sky, making them eventually difficult to study. So now that we understand, and I really do hope that you do get the point of what astronomical seeing is, let's jump to the objective of the internship. So the first objective was to design the dome enclosure for simulation. Dome enclosure is the housing that surrounds the telescope. In this picture, you can see the external dome enclosure of the 3.6 meter Devstal optical telescope. What we wanted was to simulate how the air flows on the top of the dome and find out the effects of dome seeing because of it. I had to design this dome enclosure in a software and then eventually use it to simulate the air that flows on its surface. Second was to find out how much dome seeing value was, to quantify it and know how much it is, so that when we give our engineering ideas and we see and simulate, we know where we want to go and we can compare those two values before and after the simulation is completed. The third objective was meshing the design and using it in the CFD analysis to find out our pain areas and how. So in the next, eventually the 3 slides that we have, I will be going through each of these objects and objectives in detail and explain how these were accomplished. So I hope that is clear and we can start to talk about the mechanical design. So our first objective was to create a mechanical design of the 3.6 DOT dome enclosure. We used NX Unigraphics 9.0 version to do it. The reason for choosing NX was that both my guide and I were familiar with the software. However, that does not mean that this software is the only one that you can use. For designing, you may also use CATIA or SolidWorks, but it is important to note that you don't need to learn all the software that are there for CAD designing. Just one would do if you learn it properly, because honestly, the features remain the same across the software. What changes is how you give those commands. So coming back to this picture that we have, you can see there is the housing of the telescope or the dome enclosure. There is also a 4-meter slit opening which opens up at night for the telescope to focus on a particular part of the sky and captures as much light as it can. This gives us a precise and high resolution image. The facility also had large ventilating fans that made sure that the temperature inside and outside the dome is regulated. So, why do we do that? We do it because the change in the temperature results in an airflow, which in turn results in astronomical seeing, and we don't want that. For this model, we only considered the natural convective heat transfer, and it's calculated by using the standard formula that we used to have in BTech, which was QA delta T. So, very simply, we've just calculated the heat flux that would be generated by this model. So, once we have this 3D model ready, the next step for us was to quantify the dome scene. And for this 3D model, you might notice that we've used a number of different features, which can include extrude and shell for sure, to make sure that it's very much synonymous to the real time dome enclosure. So we wanted to be as close as we can of the real thing so that our results are usable. So coming to the next part, the other objective was to quantify the dome scene. Now, let me put it up front. This is the astronomy based part of the internship. It's a bit tricky and a handful, so please bear with me, although I am pretty sure that you will find this interesting. So, on reading around 27 research papers, I found that there were two values that I needed to calculate in order to get the atmospheric seeing value. So, the first one is called Freed's parameter. What is Freed's parameter? It's denoted by R naught, and it is the measure of quality of light that passes through the atmosphere with changing of the refractive index. As you can see in the figure below, the turbulent air can be divided into multiple sections or wavefronts. This helps us calculate the length of turbulent air region, and we have named it as R naught. The other value that I learned about, which was important for us to calculate, was refractive indexed structure constant, also given as CN. Now it shows the atmospheric turbulence caused due to two factors. First, the speed of air, and second, the change in refractive index. Now, since it's a constant value, we have a graph that is used in many studies. Here you can see the bottom of the graph represents the ground. So as you go up, 2 kilometers, 4 kilometers, 6 kilometers, and so on, the refractive index changes for different atmospheric layers. So these constant, along with multiple formula, helped me calculate the seeing effect and properly quantify it. Now, just a small nugget of advice here. If you get a chance to work in such an internship, do realize that there are many things to learn beside knowing your basic CAD and simulation software. Although, of course, it would depend on the project that you would be undertaking. Some might require you to learn programming, and that's okay. So, one way to make sure that you have good knowledge about what's expected of you is to email or call your mentors or project guides before applying or joining the internship and ask them for specific details about what you need to know before you apply or start the internship. And that would give you an edge. I can definitely vouch for it. So I hope this helps you figure out on essentially building up the required skills and making sure that you are more than prepared when you reach or start your internship. So coming back to the presentation, and let's move to the third part of our internship, which is meshing and CFD analysis. So for our simulation to be effective and for the results to be as close as the actual scenario, we needed real-time data. So we captured many parameters which were then used as input for our simulation. So I was sent to Devsthal for an evening and the other morning. I'd say I was there for a day. And I was asked to take various readings starting from 6 p.m. till 6 a.m. in every 2 hours. What I recorded is here on the screen. So we recorded the inside and outside temperature of the dome and used these as the temperature input for our simulation model. I also recorded the velocity of air inside and outside the dome, along with the wind direction to make sure that we have a range of velocities and directions to input in our simulation. So Devsthal Optical Telescope is actually situated at the top of a mountain, which to be as close to laminar airflow as possible. So we found out that the velocities were again lower and in the range of less than 5 meter per second. And it was decided that what we'll do is that we'll simulate for the input of 2, 2.5, 3, 3.5, 4, 4.5, and 5 meter per second air velocity. But before we punch in these values in ANSYS CFD, we needed to mesh the design for accurate results. For those of you who are not familiar with ANSYS, it is a simulation software that works on finite element analysis and the Navier-Stokes equation, which means that you need to transfer your design from a design software, in this case, NX Unigraphics, to ANSYS CFD so that the software can break the design into small called elements and make it easy for the software to run it for you. Here is the meshing for the dome enclosure. You can have a look at it. As you can see on the top left, the flow domain covers the entire model. It is basically like a wind tunnel that we have created to simulate the wind passing over the dome. That is why you can see that there is an inlet and outlet, which determines the direction of the wind. So remember, I did note the direction of the wind when I went to the Devsthal Optical Telescope site. So that was again used as an input for our simulation model. We have the dome enclosure in the middle, which again is also meshed. The total number of nodes and elements are mentioned on the slide, which is just to give you an idea of how tedious this simulation exercise was. Each simulation took about 25 minutes to run. And God forbid, if you have put one input wrong, you have to run it all over again. So for the ones who are not aware, elements are those small triangular pieces that you can see on the mesh. And elements is when two nodes connect together, the elements and nodes together form the mesh during the meshing inside ANSYS. Now, some people also use separate CAD software or separate meshing softwares to do this exercise. But I, in my experience, found that ANSYS does provide you a good enough mesh to work with, depending on how big element size you want and how do you want to go about with your simulation. So coming on the results that we got. So we got multiple results for multiple velocities like I've talked before. But today I will be focusing on the results that we got with air velocity of 3 meter per second, because those results were the closest to the actual data recorded. Here are the contours or multicolored graphs that are generated after the simulation for various important parameters is completed. So the first contour that we generated was for the pressure contour. So have a look at this graph as a whole. you will see those problem areas that I talked about. There is a light blue color region at the top of the dome that you can see where low pressure is formed. Now, this area shows it, and we started recording the pain areas of the telescope. The second one narrated was the velocity contour. With the light blue region that you can see is from where the air enters the dome, and that is through the 4-meter slit opening that we have on the telescope. And you can very easily make out how it exits the dome on the top, creating a turbulent flow design, which is honestly not what we are looking for. We're looking for laminar flow designs to make sure that we have a balanced situation happening for the telescope which is inside this dome. So again, we were able to note the pain point. Next is the temperature contour, which shows the changes in the temperature inside and outside the dome. Here at the right side of the enclosure, you can clearly make out the difference in temperature due to turbulent air. Remember, we used to study about vortex, and that is what is the kind of air temperature uh, that we can see on the graph indicates. And lastly, what we had was the temperature gradient contour that focuses on how the temperature from the neutral ground level goes to the top inside the dome enclosure. Because let's face it, ground too is a heat source. So that needs to be accommodated in these models. These contours were generated from airflow results. And I also have a small video to show you how that works. So in the next slide, take your time to understand what's happening, and I will run it twice for you to just have a look of what the simulation looks like in ANSYS. So let's play back one more time. As you can make out, the spheres represent the flowing wind on top of the dome enclosure, while their color indicates and corresponds to the velocity. This specifically helped us locate the problem areas in the dome that made us realize that we need more ventilation, and there had to be some kind of a design modification in order to minimize the temperature inside and outside the dome. So as per this CFD analysis, you have it as a supporting data. I've seen people and undergrads using the simulation software as the Bible. You put in data, you get data out, and you believe the simulation results are as close to real case scenario. But that's never the case. To make sure that your simulation matches very well with your real-time efforts, make sure that the input that you're putting is the real-time data. And also, you need to have hand calculations. Now, this, I cannot stress more on it. It's seriously very important that you have hand calculations comparing what came out of the software and what was expected. Because this gives you a lot to compare and understand why the simulation that you are working on is not the final deal. You need to have some clear idea of what the simulation is showing and what actually is happening. So, as per our CFD analysis, we were able to find the following results, and I hope you understand this from the project objectives. The unstudied CFD simulation model that we had performed was greatly accurate and can be used for optical telescope and domes. The maximum value after all that we had conducted came out to be 0.59 arc second. So if you remember my first slide where I was talking about astronomical seeing, This one is less than 1 arc second. So it's said to be excellent, right? However, just to emphasize, there are better optical and ground telescopes in countries outside India, wherein they have clearly mastered the art of making sure that there's no seeing for their ground telescopes by heavily investing in the infrastructure. So that was not the case with these telescopes in India, but the what we saw probably came under suggestions of how to improve it. So the inlet speed within 5 meter per second and vertical temperature gradient for the air produce an average of 10 base to the power minus 15 refractive index fluctuation. So this was another thing that we had calculated using the constants that we discussed. And lastly, of why I was there as a mechanical engineer was to provide the engineering suggestion. So remember the pain areas that we talked about? We noted that forced ventilation in these areas by using external wind flow sources, which can be either fans or radiant cooling systems, will greatly decrease the amount of seeing. So this can be as good as an observatory in maybe Hawaii or in Argentina, because those were the reason why we got the maximum value of dome seeing as 0.59. So these were the engineering suggestions, at least from our end. And I hope this helps you understand what the project objective were, how we dealt with each of them, and how was the result interpreted. So moving on, as I promised, I have a slide deck for useful links. So please feel free to take a screenshot or click a picture of these useful links for everything I had talked before. This will help you learn about opportunities for mechanical engineers within the astrophysics and space science domain. However, if you're not able to capture the screenshot, no worries. I will be sharing these links in my next LinkedIn post. So here also you can notice I have mentioned and specified links for space, for upcoming asteroid search campaigns, the simulation online learning course on EDX, and also for the courses that you can find on EDX, Crossera, Indian Space Society, and I've given the links for visiting student program at Aries, programs at IIA, IUCA, and IIT Indore, which I'm happy to note are offering virtual internship opportunities. Not just these, but many more. These were the ones that I could find online. And lastly, I wanted to share where I'm at in my astronomy journey. So, besides working professionally in a domain which is slightly different from astronomy, I occasionally make time for overnight sky observations and even for observations in general. For example, in December 2019, before COVID happened, I visited Kasaragod in Kerala to witness the annular solar eclipse, and it was a wonderful experience, which not only gave me a chance to see an almost perfect total solar eclipse, but also introduced me to a new place where I experienced a wonderful culture and took back home many memories. One such event that is coming up is the ETA Accurates Meteor Shower. It will be visible in Delhi from 5 to 6 May. However, it will be visible most parts in India through the month of May. So you can check online whether you can observe it from your location. So that's an event coming up for all you amateur astronomers out there who would like to have a look and enjoy the event. And lastly, if there's anything I want you to take from this webinar, it is this, that there are more ways than one to keep the spark alive. You can be a mechanical engineer in making, or someone who's currently working in the domain that you don't find very lucrative. But that does not mean that your curiosity needs to be restricted to one place. There are many ways in which you can upskill yourself to enter this domain. And I hope you get some we got some ideas from today's webinar to do just that. So thank you all for taking out the time, and thank you, Samarth, for giving me the opportunity to share my experience. I really appreciate it, and thank you all for listening.
Okay, so that was amazing. And thank you very much, Sanchita, for accepting our invitation and coming forward to share your successful experience with the world. And I would also like to appreciate Ms. Sanchita's goodwill to give her precious time and conduct this webinar without charging a single penny for it. And hence, we are able to put it completely free out there for any and every aspirant, which will help them to eventually grow in their career.